all. Welcome to the Munro podcast. I'm Tom Pruchet, your host for today, and we're here today with some gentlemen from Wolfspeed and Texas Instruments. So from Texas Instruments, we have Mark Ng, Sector General Manager, Hybrid and Electric Vehicles. We've got Jonathan Hayes from Wolfspeed, Applications Engineer, as well as Ty McNutt, Director of Product Marketing and Power Modules at Wolfspeed. So welcome, guys. If you don't mind, if you could go around and kind of tell us what your roles entail and maybe just a little bit about your background, we'd all appreciate that.
I'll get started. So my name is Mark Ng, and I'm the General Manager for Electrification and Body Electronics inside of TI. So what I do is I have a team of system engineers that work directly with all the car manufacturers as well as their tier ones on next generation car designs, whether it be for battery management systems or traction inverters or DC to DC converters and such. So we're working with our latest generation devices and next generation designs which are hitting the road, let's say in 2025 and beyond.
Ty McNutt, Director of Product Marketing for our case module product line here at Wolfspeed. Spent 25 years in silicon carbide device design, package, and product development. And currently the team represents the case and standard power module product line targeting industrial, energy, and automotive applications.
All right, Jonathan.
Sure, Jonathan Hayes. So I am an applications engineer and I lead a reference design and hardware team for our case power modules business unit under Ty's leadership. So my role is kind of, getting into the nitty gritty of the technology, working with our partners like TI and developing these reference designs that we'll be talking about today.
Right, and yeah, that brings us to those reference designs. So, I'll give a little bit of my own background here as Director of Electrification from Munro. My background is electronics and controls. I did a lot of embedded systems development through many years, and the last 17 years focused on the electrification business. So it's been a wild ride for me, but I am very familiar with the reference design concept, and our viewership may have some familiarity with that. But in my experience, reference designs can be critically important to the development of a new product because it gives a developer a huge head start on whatever they're trying to design. And from what I've seen so far, the inverter reference design that we're going to talk about here mostly is a great example of that. It looks like a fundamental building block to build a lot of different systems that I'm sure your customers and Munro customers and viewers alike would all appreciate. So let's talk about that a little bit. So, what was the reason for the reference design? Did you, is it just kind of a mandate that you do this, or was there a specific need, or I don't know, maybe a client that drove it? Maybe I'll pass that to Mark. He looks like he's got the smile ready with the answer. So,
sure. So I'll take a shot, and maybe Ty and Jonathan, you can try as well. But within Texas Instruments and Wolfspeed, we really have all of the components which are necessary to make a traction inverter. If you look at Texas Instruments, we've got the entire portfolio, whether it's the microcontroller, which is actually running, I'll show you this later, this FOC or field-oriented control for the inverter, or you're looking at the gate driver to drive the silicon carbide modules, which you guys have featured in your videos on these teardowns and so on. Whether it could be bias supplies. But one of the things that we really need to make a traction inverter work is the silicon carbide module. And so we really wanted to partner with a leader in the industry, which is Wolfspeed. And their XM3 modules are used in all the latest generation traction inverter designs. And essentially, we wanted to, together, create a platform that our customers could immediately test and get to market really quickly. So we basically, that was the goal, is to basically, show how to get a working high efficiency design out the door.
Nice. And guys, you have more to add to that? I'm sure there's different perspectives from different views.
Yeah, certainly. That Mark summed it up very well. Partnering with key leaders in the field to bring automotive quality products to market is what we've done here. And with the XM3 module, we've designed the module such that the silicon carbide devices operate as fast as they can, as efficiently as they can inside the module. And so what we wanted to do with the evaluation kit was start to build on that so we could show the customer base how to put the proper busing with low inductance, capacitor selection, your thermal characterization, and cold plate all go together to give you an efficient system. And then coupling that with the silicon and logic from Texas Instruments, we're able to show the whole package to the customer. Then they can take that reference design, they can iterate it, put it in whatever form factor, volume, and that they need for their system to productize it and take it to market. So it really is a nice teaching tool to get started with silicon carbide to make it easier. And it has all of the software and capability as well. So it's a very nice way to start. But as Mark said, all of the components then can be taken directly to production. So it's a very nice leap from scratch to get going as a customer.
So I would like to add one thing, which is, we can talk about technical mumbo jumbo all we want, but the reality is that with the amount of electrical vehicles that are hitting the road, it's, the car manufacturers are all, in a way, new to electrification. And so whatever help they can get to get these designs working is critical. For Texas Instruments, we've been a chip supplier, a semiconductor supplier. You've heard about that in the news a lot, right? But it's very hard to just sell a chip by itself. And so that's kind of the goal with these reference designs. But we also wanted to take this one step further in allowing our customers to actually see what happens when we have the entire ecosystem together. So what happens when we have our chips working together with a leading, industry-leading silicon carbide device? What is the efficiency that you can get? What is the, how many RPMs can you get to? How much maximum power can you get to? This is a fully tested reference design, which we did on an inductive load test, as well as on a motor emulator, which we can show you later.
Jonathan, I don't know if you have anything to add, but certainly weigh in if you do. We have a PowerPoint presentation, and I've got a number of different video clips that I've looked at. So very impressed with the way it comes together, very simple to assemble, very easy to understand. Something that, again, should be a huge shortcut for the developers of such products. Let's talk specifically about this silicon carbide 300 kilowatt, 800 volt inverter. So again, it's a traction inverter. It's meant to provide the propulsion force of a vehicle. 300 kilowatts is a good start. That's, in the ballpark, if you will, for your base level EVs. I'm kind of a performance enthusiast, so I like that it's, 300 plus, if you will. That said, it's clear to me by looking at it that it's not solely intended for traction drives. With a different positioning system, if you will, instead of using the resolver to measure the angular position of the rotor in a traction motor, you could probably very easily change that front end so that it monitored 50 or 60 hertz and use it then for a stationary power inverter application. Is that a good statement? I mean, I don't want to pigeonhole this into just traction drives if it's not solely intended for that. So what can you say about alternate purposes and your intentions behind this reference design being used for those purposes? Any thoughts?
Yeah, I would say certainly that the three-phase inverter can also be used as a rectifier, and then with that coupled to piece together yet another three-phase inverter to be a motor drive, right? So you can think about it as an active front end in certain applications to drive a motor. There are a number of other applications on the industrial side, and you're exactly right. With a few tweaks and iterations on the software and how you operate the system, you can easily start to test in some of these other applications in your laboratory very easily.
Yeah, Ty, myself, Jonathan, I think we've all been in industry for quite a long time. One of the things you'll realize is that this technology actually gets reused everywhere. So these concepts, which are maybe in industrial, like an energy storage type of application, get reused in automotive, which, I used to work on server power and before that working on telecom stuff. A lot of the concepts that we see in auto today are really just build-ons on top of these markets, right? So technology just continues to evolve. It's kind of the materials, the material science, the silicon carbide, these wide bandgap materials, which has enabled an explosion of different types of applications.
Yes, it's an exciting time to live. It's as a developer watching silicon carbide evolve. For years we could just get the diodes, and everyone wanted the switches, and then it was like the holy grail, and then suddenly Tesla put it in a traction inverter, and it kind of pushed it over the hill, and now it's gaining steam. So, been watching Wolfspeed, Cree prior to that, and it's really exciting to see it finally manifest into real products for me personally. So, again, thanks for pulling that together. Now, one of the other backgrounds I have is model-based design. My world was mostly, in simulation with MATLAB and Simulink and things like that. And I saw in the presentation that, there's at least an accommodation for code like that. The field-oriented control is a good example. These are things that could be intellectual property for your clients as they develop unique attributes. And, I'll kind of give an example. A lot of folks think about a permanent magnet synchronous machine motor, 3-phase drive, hook an inverter to it. Oh, look, it spins. You're ready to go to production. When in fact, there's a lot of tuning involved, a lot of optimization. So, what can you talk about with regard to how your clients, maybe Munro's clients, could actually use this as a platform for developing their own intellectual property? I gave a couple examples. Maybe you can toss out some tools or methodologies that you've used for tuning, maybe even have some thoughts about specific examples. So I don't know. Again, model-based development, customers developing their own stuff. Here's a wonderful hardware platform to do so. It looks as though you may be giving them at least a good head start in software. And again, so it's kind of an open topic here regarding your clients in developing. You want to take that on here?
I can take a couple of, yep. I'll make a couple points here. So the inverter reference design, which you can see, throughout the video, is really a programmable platform. So at the heart of it is the silicon carbide, but it's also being driven by Texas Instruments, microcontrollers, which are programmable. And they then drive these gate drivers, which are, efficiently driving these wide bandgap modules. The nice thing about the microcontroller is that it runs a high-speed loop, and the reference design actually allows you to hook up to any motor. So, in fact, one of the things that we did here was we did basically inductive load testing, and then after that, which inductive load testing is basically kind of testing the power stage open loop. You're not really getting any kind of feedback for rotor position or anything. We actually moved this into a motor emulator or a hardware and loop simulator, which we can show you pictures of later. And in that, we put our own a real motor model into it. And so using this platform, one of the really cool things is that you can tweak it for whatever motor that you want to run. And you can test it to whatever standard, whether it be like a worldwide light harmonized passenger vehicle standard or a China standard or whatever. The platform really allows for IP development, intellectual property development. You can have, using TI's basic, control algorithm together with, your own IP, you can make it do virtually anything that you want to any motor that you really wanted.
All right, nice. That's exactly what I was hoping to hear. So
I can add something as well.
Wonderful. Please do.
Sorry to interrupt. Yeah, so just speaking from the power module side and the power semiconductor, you mentioned model-based kind of development and simulation. One thing that we really like as a company is the Plex simulation environment from Plexim. So what this is a electrothermal simulation environment where we fully characterize the power module, the cold plate solution, TIM, so the entire power stack up thermal management solution, and we can model that, and we can model the electrical performance of the semiconductor, so customers can then take this model and run a system level simulation for their particular operating points and understand, the bounds of the performance that they could get out of not only our modules but this particular reference design. So that's one thing that we really like to push, and that's a tool that we use, and we provide all of those models and information so that our customers can use as well to then work in coordination with what Mark said in terms of the control side. They also have that electrothermal simulation side.
Very cool. So, let's talk about some of the major pieces of code that go into this thing. Mark, you mentioned field-oriented control. That's a big one for me. Just a little bit of background on that. You've got an electric motor. When you drive it, you can appreciate a more constant torque up to base speed. And then beyond that, there's a little bit of magic that's involved with field weakening or flux weakening to try to take it beyond the base speed. And in some cases, maybe 2 or 3 times higher than base speed. So this kind of is an example of what that intellectual property might be based around is when you get up above that base speed, it's difficult to keep your efficiency without some really accurate tuning. So my question is about the field-oriented control. Is this also part of the reference design where someone has a good head start on that? Yeah, Mark, you mentioned earlier, so tell us what you wanted to say about field-oriented control.
Well, I think you know a lot more about field-oriented control based on what you just said, but yes, there are a lot of bright people inside of Texas Instruments that have written the FOC algorithm. And that is available for free as part of our motor control software development kit. And that is basically given out as part of this when you purchase the kit. But essentially, the FOC control algorithm has to run on hardware, essentially these microcontrollers that are incredibly fast and have very fast what we call real-time control loops. And with that, you're able to run at, let's say, 20K of RPM, which is actually what we achieved here, or 300 kilowatts of power. So it's not easy to achieve a high performance inverter because you need basically a very good control loop running on a very good microprocessor. And then you also need a very good power stage, which essentially are these silicon carbide modules. So
very nice. So it's great to know that that's considered as part of the design and something that people can use as a springboard towards their own version of that. Another statement about inverters, a lot of people don't think a lot about the efficiency and how it affects the system, but it's one of my things I like to remind people of is that efficiency is sort of a multiplier in the system. You can talk about having your 95% efficient motor, but you have to have a high efficiency inverter to be able to realize, anything close to that. So, I love to use the example of if I have an 80% efficient motor and an 80% efficient inverter, I've got a 64% efficient system with their coupling because it multiplies. And that's not really intuitive for a lot of people, but it kind of, heightens the importance of understanding the role the inverter plays in the traction drive efficiency and ultimately, how many miles you can get from a given battery. So, let's talk about the efficiencies you've achieved. You've got a lot of work that you've done with motor emulation and a lot of data that has come out of that. So, you hear a lot of stories about efficiency being a fixed value, but we all know it's sort of a map. It's a function of speed and load. So let's talk about efficiency. What sort of efficiency achievements have you made so far with this design?
So I'll start there first. Maybe I can let Ty and Jonathan speak about it because I've actually got some really cool slides that I'd like to show. to show you the results on it, but maybe we can talk about it first. In general, the key highlight for this reference design is, number one, the silicon carbide device from Wolfspeed, and number two is we have a brand new technology in our gate drivers, which is able to fully utilize what we call adjustable gate drive strength. And without geeking out, right, it's basically putting the silicon carbide into a very efficient region to switch it really quickly without stressing it too much. And when you drive it quickly, you're able to get more efficiency out of the inverter. Your question about how much efficiency we were able to gain, I'll answer that first, and we can kind of get into it. But essentially, we were able to get a 2% gain on efficiency, and I'll show you how we got there. And it may sound like it's not a very big number, but it actually correlates to a very big gain, whether it can be a reduction in your overall battery size. You don't have to pay as much for a battery to get the same mileage. You can actually get more miles per charge. You can actually, save cost and get more miles per charge. So I'll talk a little bit later about, what that 2% gain in efficiency is, and I'll show you how we got there. But maybe, Ty, Jonathan, do you want to add a couple points before I share some data?
Yeah, I'll reiterate what was stated about kind of daisy chaining the efficiencies. I think that's one of the things that we wanted to address with this design, is that not only do you want to look at just the inverter efficiency, but you want to look at the inverter coupled with the motor efficiency, and then also the load profile. So that's where we take it all the way from understanding the losses of just the inverter, doing the inductive load bench testing, and then taking it all the way through hardware in the loop testing, and then motor emulation and drive cycle testing, which Mark is going to show how we got those efficiency improvements. So I think that's a really big point that we are emphasizing with this design, and showing the capability across the entire design cycle that a customer would go through.
All right, very cool. So, silicon carbide, one of the real big reasons everybody wants it, if you will, it reduces the losses, the switching losses, if you will. And everyone wants to drive higher and higher in frequencies, which means you're switching more and more often, but you lose overall efficiency because of these switching losses as you do that. So I saw in the presentation there were 4 different frequencies that you applied, and I think, Mark, as you mentioned, you achieved a 2% improvement. What was that compared to, just for our audience sake here? When you say a 2% improvement, compared to what?
So we look at, and you'll see it in the data later, but we look at basically using just one gate drive strength across the entire drive cycle. So when I talk about drive cycle, there are these standards like the WLTP or CLTC. These are just basic standards that each region around the world has, and it basically says that for a given duration, what is the RPMs that you need to achieve. It's kind of like when you bring your car to, I guess, a smog test or something. You're kind of accelerating and decelerating. There's a standard that you have to go by. The way that we took this data was we said, okay, if you apply the same gate drive strength throughout the entire drive cycle, that's your baseline efficiency. But let's say when you drive a car, there are some times when I'm driving in, let's say, low RPM mode, maybe in city traffic. That's when my motor and my inverter are actually least efficient. And when I'm kind of driving in the highway and such, right, that's where I'm getting more output power, and that's where the motor is more efficient. And that's where, in general, the overall inverter is doing quite well. One of the things that we're doing in this reference design is actually toggling the gate drive strength such that when it's in low RPM mode, below a certain current threshold, I'm using a certain gate drive strength, and above that, I'm using a different gate drive strength. So I'm actually switching faster in certain areas so that I have less switching losses. And that ability to switch faster basically gives me that efficiency gain, or a gain in switching loss.
So that, just to paraphrase that, if I understood you correctly, then the 2% gain was just solely as a function of the variable gate drive strength, if you will. So that's remarkable, because even comparing it to some other state-of-the-art silicon carbide inverter with fixed gate drive strength, then you've got a huge advantage. And those who have familiarity with the combustion engine world know what it means to gain 2%. That's a big deal. So,
Right.
yeah, very, very good.
Yeah. Silicon carbide, I would say, in just in general, over the IGBT technology in silicon, you eliminate that on-state voltage drop with that P-in junction drop that you see with the IGBT. So for your light load conditions, silicon carbide gives you a much more efficient capability. And then when you couple in the technology here and start to get that additional switching savings over the whole drive cycle, you're seeing a lot of efficiency savings, which, as Mark was saying earlier, are going to save you on the battery, less battery per vehicle, or longer mileage and range per charge. So over the whole drive cycle, we think silicon carbide provides an outstanding decrease in the losses, whether your conduction losses or switching losses, which is helping efficiency on all the different modes of operation.
All right. Again, at the risk of geeking out a bit here, this, variable gate drive strength feature has a lot of other implications. I mean, yeah, the one that's meaningful to most people is, an improvement in range, and up to 2%. That's great. However, there's other benefits. For example, improved EMI. So a lot of people don't realize that a switching device, you tend to think of it as an on-off device, and if it truly goes from on to off, there's a rise time that's very vertical in its look and feel, if you will. If you look at it on an oscilloscope, it looks like the straight edge of a square wave. But what a lot of people don't realize is, those edges are rich in harmonics that radiate in a lot of different ways or conduct, and that can translate into problems with radiated emissions, RF communications, the ability to have an AM radio that works, that sort of stuff. That is remarkable to me that you can use this for that purpose. And it's also for management of overshoot, and I assume ringing too. These are things that happen. You've got a lot of stray inductance, a lot of stray capacitance, and these things all weigh in like little oscillators in the circuit. So by managing the variable drive strength, you can put some mitigation on those concerns. Tell us a little bit about that. These are real world problems, and how unique is this variable how unique is the variable gate drive strength feature? Is it an exclusive of Wolfspeed, or are others trying to catch up to you quickly on this, or maybe it's really more of a TI invention? Help me out, enlighten me on that.
Yeah, so the variable gate drive strength is basically a feature that is part of the Texas Instruments gate driver called the UCC 5880. And you can actually go ahead and Google it. But this is basically a novel idea that we had about a couple of years ago. And I would like to say that we were first in industry to do that. We, of course, worked very closely with Wolfspeed to define this feature. And we continue to work with Wolfspeed throughout the next development cycles and so on. But in general, this is a feature that differentiates us from the rest of the industry, because you're right. If you look at a traction inverter, noise, radiated emissions, it's a big issue. And you're in an inverter, all you're really doing is basically taking a DC voltage and creating a three-phase AC waveform out of it. But in that process, like you said, you're switching the silicon carbide very, very quickly. You're having lots of overshoot. The risk of having, EMI or damage to isolation barriers, or damage to other components is very high. And having this kind of adjustable gate drive strength, or sometimes in industry we do like slew rate control and such, it's just a way to kind of control those types of features. So that is basically an area of innovation that we brought into the market with the UCC 5880.
Okay, let's take a deeper dive into this reference inverter design. There's a presentation we can follow, and we'll let Mark and Jonathan lead the way here. Go ahead.
Okay, Jonathan, let's go talk about this reference design that we did. It's called TIDM02014 on our TI.com website, also known as this 300 kilowatt traction inverter reference design. So, Jonathan, one of the things that's really cool about this reference design is it's complete. So you can see here the entire setup. You can see basically your DC voltage that comes in directly here, and it hits all of the semiconductor devices, including the silicon carbide modules, which are underneath here. And so working clockwise, what you'll see is the MCU or the microcontroller board. So we have these various microcontrollers, whether you look at C2000 or a device called Citara. This is kind of a card that slips in here. And we talked about the FOC control. This is that device that runs the FOC control that runs the entire inverter, taking the DC bus voltage and transferring that into a three-phase AC waveform. Here is the gate driver board. There are 3 of them. And basically connected to 3 of the XM3 gate driver modules from Wolfspeed.
Which are
and then
half
you'll
bridge
see
devices, right? I don't mean to interrupt, but just to kind of clarify,
correct.
that's why there's 3. Normally there's 6 switches for a 3-phase control, and each one of these modules provides the north and south switch, if you will. So just clarify.
That's correct.
Yeah.
Yep. And so there's basically 6 gate drivers in here as well for high side, low side, high side, low side, high side, low side. So you have basically 6 gate drivers across the entire 3 half bridges. And so one of the really cool things we did when we were in Arkansas was basically taking apart one of these modules and looking at what's inside. You can see the composition of exactly how these modules are made and how it looks like in die form. So the other thing we have are basically current sensors that are located underneath here. So with that, we basically have a system that can drive a motor, right? We've got the brain of the system, we've got the DC bus voltage, we have basically the position sensing input, and then we've got the current sense to be able to have all the information necessary for my FOC control. So what we have here is the exact part numbers, and I won't get into it, but as I mentioned, we have the microcontrollers, the voltage sensors, the silicon carbide modules, which are the XM3 modules, the current sense lines, which are coming across from all 3 phases connected to here. We have the resolver front end, so we have motor position coming in directly here, and then we've got the CAN interface, which is really important for later because we'll show you how we connect to the e-motor emulator or the hardware in loop simulator. We talked a little bit about FOC control, and this is getting into very nitty-gritty details, but essentially FOC control is basically taking your angle and your speed together with your DC link voltage as well as your phase currents to generate the PWM voltages necessary to the gate driver, which then drives this motor. So you basically have a closed loop control, which is taking into consideration your various factors, including voltage, current, angle, and speed, right? And along the way, you have to look at, temperature, your motor temperature limit, and your silicon carbide temperature, because you want, you're talking about human life, and so this is kind of a safety type of application. So, we have to run the diagnostics, in parallel with the driving of the motor.
Now, I should point out that lower right-hand corner on that slide, where the resolver measures the angular position speed of the motor rotor, that would be in a stationary power application like you'd use for, grid energy storage inverters, large solar inverters, whatever. That would be one area that would change in hardware so that you could monitor the 60 or 50 hertz that's used for the grid. So, it's a nice modular piece that could be switched out relatively easy in this reference design. So.
Well, like we said, I think a lot of this application, it's applicable to almost everything, right? So these resolvers, position sensors, right? We have a lot of applications in the real world where we actually have to monitor the position of the motor in relation to speed and so on. So even like when you roll down your window or any kind of basic motor type of application or different frequency, like a 50, 60 hertz application for industrial, yeah, you would have the same kind of setup. And in that respect, this design could easily be used towards other types of energy storage or other types of industrial designs.
Very good. Thanks.
Jonathan, do you want to maybe take this one, why don't you take a shot at this one?
Sure. Sure, yeah. So this is our e-motor emulator test setup that we have in our lab in Germany, in our Wolfspeed lab, to clarify. And so, this is a great, test capability that we have in-house that we're obviously taking advantage of, with this reference design and proving out the system, both from the power semiconductor and from the TI solution set. So we started in Arkansas with our inductive load test bench, but like Mark previously mentioned, it's kind of just a simple inductive load. There's no real closed loop control going on, and really just exercising power on the entire unit. So the kind of a first debug step, and then this is that next level where we can actually put this in this test system. Take measurements on an oscilloscope, use the power analyzer to get the efficiency data of the inverter under test, and of course the e-motor emulator to emulate that motor, so we can kind of get these performance curves, which is very critical for the traction inverter reference design.
Yeah, the motor emulator makes it hardware in the loop, if you will, so to speak. A subject near and dear to my heart. This would be, again, where you might change the thing you're emulating. It's still going to be a three-phase device, but various sizes of motor can be emulated. And wow, how much easier is it to do it in the virtual world than to actually have to switch in the real motor, especially a motor that may not exist yet. You may still be in the design phases of that as well. So
that's right. So that's one of the. This is one of the reasons why TI and Wolfspeed partnered together, because a lot of people do the inductive load testing, which again is a kind of an open loop test. It's kind of like, okay, my power stage can run like this, and I'm not looking at rotational angle or position of the motor. But it's not until you actually close the loop of the system that you are actually able to measure the efficiency of the power stage, like this 80 and 80%, right? So the efficiency of the power stage together with the efficiency of the motor. What this allows you to do, and by the way, this is a multi-million-dollar setup. Basically, it allows you to put a motor model into the system, and it emulates that motor. So I'm not having to drive a real motor, and I'm able to extract the actual efficiency of my power stage controlling the actual motor, and you'll see some of those results later.
So yeah, here we're looking at the inverter actually inside the motor emulator test bench. So you have the connections of the power, the DC plus and minus coming in, the three-phase motor connections coming from the inverter, and then into the e-motor emulator cabinet. And of course we have all of the auxiliary components around it, cooling system, because that's actually a fairly critical component to testing the efficiency is how well you're actually cooling the power semiconductor devices. And then the feedback not only is done on the inverter control board itself, like Mark mentioned, the resolver encoder temperature, but also we have that feedback into the e-motor emulator test setup. So Mark, is there anything that you'd like to add?
No, this looks like a rat's nest, but actually it's not actually that bad when you look at the waveforms, because all you're really doing is trying to take a look at the outputs, but you do need to provide all of the stimulus, right? So you're getting the angle of the motor, and basically everything is emulated by the hardware and loop simulator here. So
yeah, one person's rat's nest is another person's meticulously organized test bench. So yeah, I appreciate that.
So, Tom, you mentioned this efficiency map, and here it is, basically the result of doing all of this testing on the e-motor emulator or the Hill hardware and loop simulator. This curve looks scary, but it's really not that hard to read. Basically yellow, and it's hard to differentiate between these colors here. The yellow basically means you're at 100% efficiency. This is the highest efficiency that you'll get. And then, the blue is where you're starting to drop off. Now, this particular motor was a model this motor was given to us by one of our customers, one of our key customers out there, because they wanted to test this, and they wanted our help on this design. And so you can see that this particular motor responds as follows, right? If you're having low RPMs and low torque, that's not what this motor is designed for. What the motor is designed for is basically in this range here. If I look at this little half moon here, there's like a 99% efficiency curve here. So anytime I'm operating at this RPM and at this particular torque, let's say 9,000 RPM and 90 Newton meters of torque, I'm able to achieve 99% efficiency on my inverter. As I start decreasing my RPMs, I start decreasing my efficiency, going from 98.95, 98.59, 97, 95. And that's kind of how you read this map. Now, the really cool thing is if I was able to intelligently change my gate drive strength, then in theory, I should see the curve actually shift to the left, right? So what I mean by that, if I'm running at, for example, 5,000 RPM, and let's say this is about 40 Newton meters of torque, if I'm able to change my gate drive strength, I should see this 97.7 efficiency actually go up. So I should see these curves, if you will, these little exponential curves shift to the left. And if I look at it, if I compare slides from slide 15 to slide 16, you actually see that, right? So if I just kind of go back and forth, you're actually seeing the curve shift. So that means that in that same 5,000 RPM, 40 Newton meter of torque, I'm actually above 97.78 now. It's closer to 98. And so you're seeing that in general, everything shifted because that's the effect of the gate driver working together with the silicon carbide. And in general, what happens is when you're able to gain this efficiency, you have overall better performance, and that's where that 2% comes in.
Yeah, interesting. Of course, you have to assess the trade-offs too. If I choose to use the strong drive, I hope I didn't create some sort of an EMI problem or some other issue. So yeah, now I have a way to, through an experiment environment, iterate and optimize. So you know when to apply the strong drive and when not to.
Right, and I will mention that Wolfspeed and TI, we specifically worked together on this because we wanted to give this setup. We wanted to have our customers be able to access this setup. Again, as I mentioned in the very beginning, we as a semiconductor supplier can just provide the chips, and Wolfspeed could easily just provide those XM3 modules. But until you put these things together and put it into a real environment, you're putting the onus upon the car manufacturers to go do this and prove it. But here we're saying that here's our platform, come to our test setup, and we've got everything ready for you to go using your model. If we look at this slide, this is essentially the cumulative energy that was basically consumed in the entire drive cycle. So the red line essentially is basically the energy that was consumed by using weak drive. And then the gray line is using what we call strong drive. And so you'll see these, the energy consumption goes up, and then maybe I have some regenerative braking, so it goes back down. So as time goes up, my total cumulative energy consumed is this much, right? So at the end, I have some regenerative braking and I go down. And if I zoom in here, I get that 2% in savings. And that 2% in savings basically translates to either better consumption, which gives me better distance, or it gives me, better overall usage of the battery. And in general, what you can see here is that can be $140 of battery savings, or you could translate that to 15.5 more kilometers with the existing battery pack, or you could say I could reduce the number of battery cells and save 9 kilograms of weight, or I can simply get more space in the vehicle by reducing the size of the battery. So that 2% doesn't seem like a lot, but having that extra range or that extra, space over, the entire course of the year, just saving 15 kilometers is quite a bit of gain.
It sure adds up, doesn't it? Yeah. So interesting. Quite the reference design with a methodology for developing kind of built into it. You mentioned the multi-million-dollar test bed. It's probably worth mentioning that not everybody's going to have that budget, and I don't want to scare people off with that. There are other, methodologies that can be done to lower that cost, if you will. But this is the way to do it. I really appreciate that you guys have brought it out and shown everyone how it works. So let's talk a little bit about the switches themselves. So the module that you've used in the reference design, of course, Wolfspeed has a whole range of modules. And if you were to come to Munro Associates, you'd see our inverter table. We've got, 15 odd different inverters that are all torn apart with different technologies. And you can see the different methodologies that have been used on the switches, and we've torn them apart and looked inside, and we understand them. So this one, based on some earlier slides that I saw, or I think it was the B-roll film, this one is built on a ceramic substrate with bond wires. I just want to comment on, what is the roadmap with Wolfspeed regarding moving closer to some of the other designs we've seen that might be better for thermal performance. This is like sintering versus bond wires. Is there a sintered module in the lineup now? And if not, when do you expect one? Or is there maybe a reason why you don't want one?
Sure. Yeah. So Wolfspeed is, as a semiconductor company, vertically integrated from the materials all the way up to the packaging and discretes and power modules. We're always evaluating and implementing, the technologies out there to, best design our modules, but really to address, the market needs and what our customers are asking. For this particular module, the XM3, we've made design choices for our customers, making the trade-offs in technology and cost and things of that nature. So we're always evaluating. Sintering is in the portfolio, and of course, we're always looking at adding the new technologies to our new platforms.
Okay, good answer on that. And and I truly appreciate that. Part of the reference design is the simplicity of it. I mean, it's not very hard to take the flat bottom of this module and connect it to a cold plate, whereas if you had some sort of pin-fin arrangement that had to go right directly into the coolant, that's a heck of a prototyping exercise to try to make something work. So I truly appreciate the simplicity. And, where I've had clients that have been adamant against the use of bond wires due to shock and vibration concerns and things like that. Certainly there's a lot of applications where there are no such concerns. And this one may be quite robust, despite using that sort of bond wire methodology. Do you have any sort of a specification for shock that you can talk about, or just because this might be much better than what others have thought about with the same sort of technology in the past? So,
sure. Similar to my previous answer, we address what the market is requiring. So for this particular XM3 power module that's in this reference design, it is automotive qualified to the AQG 324 standard. So in that standard are limits for shock and vibe. So we do test to that particular standard. So really, we design, again, making all of those design trade-offs, to meet the standard that would address the market need and what our customers are asking for.
All right, good stuff. Well, we look forward to more good things coming from Wolfspeed and the silicon carbide realm. All the fervor around wide band gap is now coming into focus, and everyone is now starting to pay attention. TI, thank you. You've stepped up to the table to, partner with a world-class company like Wolfspeed to bring this to market and provide a tool chain and a surrounding chipset that makes it simple to implement. And you can at least hear it from this developer. It's truly appreciated that you've done that. So I think, are we about there? Yeah, I think this is a good way to end it. And I want to thank both of you, Jonathan and Mark, for a deep dive and a little deep dive into geekdom here, if you will. I'm pretty sure we've satisfied the interests of a lot of our viewership as well. So again, thanks, and thank all of you for watching.